Hi guys, so if you're curious about on-policy distillation, you may have heard about reverse KL versus forward KL. And in the literature, people tend to say that reverse KL is mode seeking while forward KL is mode covering. So what exactly does this mean? So today we'll be covering that. So before we start, let's have some definitions of what it means to be mode covering in the forward KL case and what is mode seeking in the reverse KL case. So mode covering basically encourages the students to cover all regions of significant teacher probability. So if the teacher assigns some form of probability mass in the area, you want the student to cover all of these probability regions. For mode seeking, we just want to concentrate on high probability teacher regions, but we are a bit more forgiving if we miss out some. So before we can understand why reverse KL is mode seeking instead of mode covering, let's take a look at the exact KL quantity. So if we look at the definition of the KL divergence quantity, we'll see that it's actually the expectation of the log ratios between the two distributions. And if we let Px to be like the teacher and Qx to be the student, then we get the following quantities for the forward KL and also the reverse KL. So for the reverse KL, we basically just swap the positions of the probability distributions. So once we take the expectations, the exact quantity for the KL loss terms will be on the right. So usually we add these values to the loss. And so what this means is that if these values are high, then there will be a higher penalty on the loss. So now we will see why for the reverse KL case, it actually is more forgiving towards not covering all the modes, while for the forward KL case, it penalizes it more. So now that we managed to define the exact value for the KL term, now let's just plot this over a single sample and see the difference between the two. Yeah, so this is the graph when we plot the exact KL values for a single sample for both the forward KL case and the reverse KL case. So to have a better visualization, let's break it down into the quadrants. So if we break it down into quadrants, so this is exactly the same as the graph previously, but what we see is that for forward KL, it gives a higher loss when the teacher assigns a high probability mass but the student assigns a low one. However, for reverse KL, it is more forgiving when the teacher has a high probability but the student has a low one, but it penalizes more when the student is high but the teacher is low. So next we'll see in a toy example how this loss actually encourages different modes. So for the toy example, we use a mixture of two Gaussians for the teacher. So here you see that there are two modes. And for the student, we use a Gaussian center on one of the modes. So this is the student model. And then we plot the exact KL loss penalty term for both the forward and the reverse KL case. So for the forward KL case, you see that when the student missed out one of the teacher modes, it assigned a very high penalty score. However, for the reverse KL case, we see that the KL penalty term is extremely low for the teacher mode that it missed out. However, there's a mismatch between the student and the teacher like probability densities at this mode. That's why it has a higher KL penalty term here. Yeah, so based on all this, we see how actually in the forward KL term it actually tries to force the student to cover the different modes, while for the reverse KL it is more mode seeking and is forgiving when the student missed out certain modes of the teacher. So yeah, so that's a full explanation of why when we say reverse KL is mode seeking and why for forward KL is more mode covering. So one final point. So one key thing in on-policy distillation is that for the forward KL, it uses samples from the teacher distribution, while the reverse KL uses samples from the student distribution. Yeah, so this would be important when we do Monte Carlo estimation in actual on-policy distillation training. So yeah, that's all the concepts we'll cover today. Hope you found the video helpful and look forward to the next one.